Hello everyone. Today we are learning exponential growth and decay. Exponential growth and decay has a certain rule, which is A equals to Ka power T. We'll slowly go through how changing each value actually affects whether the exponential function is a growth and decay. As we learned previously from our exponential graphs, for example, if we have y equals to 2x, okay, I want you to also bear in mind that I've also color-coded everything here so that it's easier for us to follow through. So if I have a y equals to 2 power x, we are looking at the corresponding values that is sort of colored in red here as well. So an exponential function has a form of like a value powered by a pronumeral. So if we have a simple equation like y equals to 2 power x for a certain value of x. So let's say the x has a domain of -2 to 3. And if we substitute these values of x into the first equation here, we will actually get a whole set of corresponding y values here. So what I'm trying to say is if we sub -2 into the first equation, it will be 2 power -2, which returns a value of 0.25. And if we sub -1, it will return a value of 0.5, and so on and so forth. So previously, we have also discussed that the values of y actually doubles, as the value of x increases. And previously, we have also talked about a value, an equation which is like y equals to half x, where this half is actually a value between 0 and 1. And what happens is if we sub the value of x, the similar value of x, into the second equation here, we will get a corresponding value of y here. And we can see that the value of y actually halves. So how does this look on the graph? The first equation, when the value of y is doubled, is actually a growth function. So we can see from the graph on the red curve over here that as the x value increases, the y value will keep doubling, and therefore we have a growth curve. If we look at the second function, so as the x value increases, the y value is actually half. So it's a decay because can you see that as the x value increases, the y value will keep halving itself. So it's actually a decay curve. So again, this curve is drawn, this graph is drawn using the Desmos function. I encourage you to go to Desmos and input in different values, and you can see whether the values is a growth and decay. But the basic guide is if the value is more than +1, it's going to be a growth curve. The base number value. If the base number value here is between 0 and 1, it's going to be a decay function. So if we look at the growth function, that's when a is bigger than 1. So for example, if there's a question, if a growth rate is r%, okay, we have to adjust the base value as 1 plus r over 10. So why is that so? That's because originally your value will be 100%. So 100, when we are converting it to sort of like a number, it's 1. So if we want to convert the percent into a number as well, into decimal, it's going to be r over 100. So therefore, if r is 20%, then my a value will be 1 plus 20 over 100. So that's going to be 1.2. So if we are talking about decay, so we always have to know that decay is between the value of a is between 0 and 1. And if the decay rate is r%, then a will equal to 1 take r over 100. That's because when you are reducing something, the value is lesser than 1. It's lesser than the original, which is 100%. So if r equals to 10%, then 1 take 1 over 100 is 0.9. So we can see between the difference between the growth and the decay is the growth function will have a value that's more than 1, and the decay will have a value that's between 0 and 1. So in this case, if we look at 0.9, we know that it has been decreased by a rate of 10%. So further understanding the exponential formula. So the exponential formula and the growth and decay rule basically have the same rule. So if we look at the exponential formula, a will be the value at any time. So this value keeps changing when the value of the time changes. So a0 is an initial value. Yeah, and we always times the initial value by the growth and decay. So if it is a growth, we have to always remember to plus it with the rate of growth. Yep, if it is a decay, we have to subtract. Yep, and r will always be the rate, and we have to always convert it into decimal place. N is the number of years, or it could be the number of minutes, depending on the unit of time that we're using for a particular situation. But today we are focusing on N as the number of years. So if we look at a question related to exponential growth, for example, if Misu has decided to invest $10,000 into a super fund, which has a return of 8% per annum. So PA here means per annum, means that if I decide to invest into a super fund, I'm going to get a return of 8% of what I've invested every single year. So this would mean that I'm getting more money, and therefore this is a growth function. So form an exponential rule for the value of Misu's fund in V in n years time. So if the question asks you for a value that's in V, we have to just rewrite the exponential rule as V equals to V0, 1 plus minus r over 100 power n. This is the original function that was discussed previously. So we know that our initial value is 10,000. So we will sub 10,000 into V0. Yep. And because this is a growth function, we have to plus, and the rate is 8%. So plus 8 over 100. We don't know how many number of years yet. So we will just leave n as it is. So if we simplify this, we will get this exponential rule over here. So for the second question, what will be the value of her fund next year? So next year will be in 1 year's time. So when it is 1 year's time, we can actually use this exponential rule, and we will substitute 1 into n, and therefore in 1 year's time, the value of the fund will be $10,800. So what about in 5 years' time? So in 5 years' time, in this situation, my n will be 5. So by substituting 5 into n here, I will get, just put this into the calculator and you will get a final value. And I've rounded it up to 2 decimal place. So use trial and error to find approximately when Misu's fund will be worth 20,000. There is actually a shorter way to do this, but in this situation, we haven't learned logarithm yet. So we will have to do it step by step. We know that because this is an exponential growth function, the value will keep increasing. So we just want to know when it will increase up to 20,000. So what I did was I just substitute the value incrementally until I get values that's nearer to 20,000, and then I will compare. So in this case, you can see that when n is 9 and when n is 10, they are approximately near to 20,000, and I can see that when n is 9, it is closest to 20,000, and therefore it will be in approximately 9 years' time. So how do we do questions that's related to decay? So let's say Miss Sue bought a brand new $1,500 laptop that will depreciate in value at a rate of 20% per annum. So that would mean that my laptop's value will decrease in value every single year by 20%. So using the same formula, we can form an exponential rule for the value of Miss Sue's laptop in n years' time. So this is the same equation, the same formula that we have talked about just now. So instead of using a plus, because it is a decrease in value, that's going to be a decay. So it's going to be a minus. The original value is 1,500, so I will sub this into here. And because the rate is 20%, I will sub 20 into my rate here, and power by n number of years. And this is at the moment still unknown, and therefore we'll just leave it. So simplifying this will give us that. Yeah. So if you want to find what's the value of the laptop in 2 years' time, in 3 years' time, all you have to do is substitute the value of the number of years into your formula, and you will get the answer. So yeah, that's the end of our lesson today. And yeah, just keep going and stay safe, everyone. See you next time.